We are now going to discuss how force and mass interact to cause motion. In our everyday world, this involves using Newtonian mechanics or classical mechanics, but this does not apply to the very large or the very small worlds. So in our everyday world, we can use Newtonian mechanics to calculate the movement around us. But in the very small world, on the atomic level, we have to use quantum mechanics for that. And when we get into the very big world, where we have very large mass or gravity, such as with a black hole, or where velocity nears the speed of light, we have to use Einstein's relativity. But for now, we're going to discuss Newtonian mechanics. Let's go over Newton's three laws of motion. The first law states that if no net force acts on a body, its velocity remains constant and there is no acceleration. The body will stay at rest or at a constant velocity unless and until a force acts upon it, in which case it will accelerate. This leads us to the second law. If a net force acts on a body, it will accelerate in the direction of the force, and that force is given by F equals ma, one of the most famous equations in history. And that will be used for most of the problems that we solve in this section. And lastly, when two bodies interact, the forces exerted on the bodies by each other are equal and opposite in direction. So for example, if I have a wall and I'm pushing on the wall, I'm exerting a force on the wall F1, and that wall is pushing back on me with a force of minus F1. So as long as there's no acceleration, the forces will be equal. There are different types of forces that most of us are aware of. These include gravity, weight, friction, tension, and the normal force. So let's go over these. So gravity, if you have two planets, you know that there's a force between them. F equals mass 1 times mass 2 times g over r squared. And that's one type of force. Another type of force we deal with is friction. And friction is a force that opposes the motion of one surface on another. It is in the opposite direction of the motion. So if you have a surface and you have a block and there's a force pulling the block this way, friction will act in the opposite direction, and usually we write that like that. So that's an opposing force. Another force that we have is tension, and that's usually in a rope or a cable. So if we have a pulley with a rope over it, and there's a weight on one end of the rope, you have gravity pulling down, but the force of tension is pulling up on that rope. Same thing if you have a block and you're pulling it in that direction, you have a force pulling that way on the rope, but there's a tension in the rope pulling that way. So that's another force that we deal with. The other force we'll need to know is called the normal force. And the normal force is the force a surface pushes up with against gravity. And it is perpendicular to the surface, hence the name normal. So for example, if you have a table and you have a weight on the table, gravity is pulling down on that weight, and that's equal to mg. But the table doesn't collapse. The weight doesn't go through the table. So since it's motionless, there has to be a balancing force, and we call that the normal force. And that force is perpendicular to the surface of the table. Let's look at one more force, and this one will be weight. Weight is different from mass. Your mass is the same whether you are on Earth, on the moon, or floating in space. However, your weight changes depending upon the force of gravity pulling against your mass. So what determines mass? Well, we know F equals ma, so mass is equal to F over A. So basically, mass is determined by what amount of force is required to accelerate an object to a certain level. That determines your mass. And the more massive you are, the more force it will take to reach a certain level of acceleration. Also, mass is measured in grams or kilograms, and force is measured in newtons, or N, which is defined as a kilogram meter per second squared. And that comes from this formula, because we're moving a mass, a kilogram, at an acceleration of a meter per second squared. So there's a difference between mass and weight is another force that you have to deal with unless you're floating in space without gravity. When we look at problems involving one or more vectors, there is a device that is used to make dealing with the vectors simpler, and that is called the free body diagram. Free body diagram. What we do is we assume that there's a point in the body that corresponds to its center of mass, and this is where all the forces will act. So let's say you have a body sitting there and you have vectors acting upon it. We take the center of mass of that body, a point, and then we assume that all the forces act on that one point. And that makes it much simpler to deal with the calculations. Now let's look at the force vector. As you can see from here, the force vector can have 2 or 3 components, and we can break each force down into those components and also look at the acceleration in each of those components. What we want to do is find the net force acting upon a body, and that's equal to the sum of all forces. So that would be equal to force 1 plus force 2 all the way out to force n. So we can do that by taking 2 vectors, for example. If we have one like that and one like that, as you know, you can take the tail of one vector, put it at the point of the other, draw where that'll go, and now you have your added vector there. Or you can break it down and use the components of the vector in each direction. So, for example, if we have a vector, let's draw a little diagram, and let's say this one goes up to there, F1 is equal to 3xi plus 2yj. And let's say the second vector goes up to here, where this is f1, f2 is equal to 3xi plus 1, 2, 3, let's say 4yj. We can find the sum of these two vectors by adding the components. So the f total vector is equal to 6xi plus 6yj. So we'll be using this technique for all the problems that we do. Let's talk a bit more about friction. As was stated, friction is a force that acts opposite a sliding force and is parallel to the surface. So if we look at a block sitting on a surface, there's a force trying to move that block on the surface. There's a normal force that the surface exerts on the block. There's the weight of the block, and we have our force of friction, which is usually shown as a small f. And so we have to include that in our free body diagrams. Now there are different types of friction. There's a static friction, and we designate that as Fs, and that's equal to a coefficient of static friction times a normal force, or coefficient times mg. And the force acting to move the block on the surface will act under the static force until the force is high enough to start moving the block. Then once the body starts moving, we now have kinematic friction, and that's designated as F sub k, and that's equal to the coefficient of kinematic friction times normal force, which again is equal to UK mg. And once the block starts moving, the friction, kinematic friction, is less than the static friction. So as soon as the block starts moving, you can actually reduce the force that you need to keep the block moving at a constant velocity. And there's also something called a rolling friction, which has to do with tires rolling on a highway, for example. And that rolling friction is related to a coefficient of rolling friction. But we won't be talking about that. Again, when showing forces on a free body diagram, don't forget to add friction, unless the problem states that a surface is frictionless or a pulley is frictionless. Now let's talk about force and circular motion. We saw in a previous video that when an object moves in uniform circular motion, its acceleration is equal to v squared over r, where the acceleration is centripetal or points towards the center. We also know that its period is equal to 2 pi r over v, and then you can find that acceleration becomes 4 pi squared r over t squared. We also know that force is equal to ma. So for an object in circular motion, if we substitute a into this equation, we get force is equal to mv squared over r. And again, force and acceleration are both pointing to the center, which means they're centripetal. A centripetal force may be due to a number of things. It could be due to gravity, friction, a string tethering a body, or even a car wall pushing on a passenger when a car is in a curve. Again, when drawing a free body diagram, make sure that you include any centripetal force along with the other forces. Some examples would be if you have a car going around in a circle. You have radius r, you have velocity of the car, the acceleration is centripetal, and we also have a centripetal force. And if we look at the free body diagram of the car, we have the car's weight, mg, we have the normal force, and we have a centripetal force. In this case, that's due to friction. Okay, so the centripetal force is due to friction, and that's equal to ms times mg. Now, what if you have a car on a banked curve? And this is going around that way. If we do the free body diagram, we again have the weight of the car. But in this case, since the wall is tilted, the normal force comes out in this direction, and we then have to look at the components of that normal force. So in this case, we have the normal force, that's the centripetal force, and the normal force in the y direction. And this is assuming no friction. So these are the forces that come into account if a car is on a highway that is banked. Now I'd like to solve some problems. There's a few things you should do when you solve these kinds of problems. First, draw a free body diagram. Second, choose which coordinates you're going to use. Usually the x-axis is put along the surface, such as a ramp, and the y-axis is put along the normal force. Third, show all the forces acting on the body in the free body diagram. Fourth, add your forces, positive and negative, in each axis. And fifth, if a net force exists, you will have an acceleration and you can find the direction of the movement. If no net force exists, there is no movement. Let's try our first problem. A 10-kilogram object is subject to two forces, one of 30 newtons at 45 degrees above the horizontal and one of 40 newtons at 60 degrees below the horizontal. What is the acceleration of the object? What is its direction? So let's draw this out. So we have one force at 45 degrees of 30 newtons and another force at 60 degrees below the horizontal at 40 newtons. And we want to know what the total force is. So we know that to add two forces, you have to add the x and y components. So we have to add F1 plus F2x plus F1y plus F2y. So in this case, we'll get our fx component is equal to F1x, which is 30 times cosine 45 degrees plus 40 times cosine 60 degrees. And that is going to equal the movement in the x direction. Mass times acceleration in the x direction. If we calculate this, we get 30 times 0.71 plus 40 times 0.5 is equal to 10 kilograms times AX. And if you work that out, you get Fx is equal to 41.3 I, which is equal to 10 AX, or AX is equal to 4.13 meters per second squared. And we can do the same for Y. In this case, force in the Y direction is equal to 30 times the sine of 45 degrees minus 40 times the sine of 60 degrees. And it's minus because it goes into the negative Y direction. And that again is equal to mass times acceleration in the Y direction. So if we work this through, we get 30 times 0.71 minus 40 times 0.87 equals to 10 AY. And following that through, we get Fy is equal to minus 135, which is equal to 10 AY, or acceleration in the Y direction is minus 1.35. So we then have our net force. The net force is equal to AX, which is 4.13 I, plus, let's take that back. It's a minus 1.35 J. So that is our net force. And if you wanted to find the direction of that force, we know that tan of theta is equal to AY over AX, which is equal to minus 1.35 over 4.13, which is equal to a minus 0.33. So the arctan of 0.33 is equal to a minus 18.3 degrees. So theta is equal to a minus 18.3 degrees. And that's our direction. Let's do another problem. A 20 kilogram block sits on a table with a coefficient of friction equal to 0.5. The block is connected to a string that passes over a frictionless pulley to a 30 kilogram block. What is the acceleration of the blocks? What is the tension T in the string connecting them? So I've drawn the picture here, and you can see the two blocks. First one on the table, the second one hanging. And let's draw our free body diagram. So if we take mass 1 we have its weight pulling down. We have the normal force the table is pushing up on. We have the tension, and we have the force of friction, and we know that the coefficient of friction in this case is 0.5. And for mass 2, we have the tension pulling up and the mass and times gravity, the weight going down. And we're looking for the acceleration. The first block will have an acceleration in the x direction, and the second block will have an acceleration in the y direction, but because they have a string between them, they're all equal. So we know that. So let's see how our forces interact in the x and y directions. So for the x-axis, for mass 1, we can see that tension minus the frictional force is going to give you that mass times the acceleration, the movement. That's in the x direction. So this is for block 1 on the x-axis. And in the y-axis for block 1, we have the normal force minus the weight is equal to 0, because it's not moving vertically. Or in other words, the normal force is equal to mass 1 times g. Now let's look at block 2 in the x-axis. Well, block 2 moves up and down, but it doesn't move left and right. So in the x-axis, its acceleration is 0. And in the y-axis, we do have some forces. We have the weight minus the tension gives us our movement of the block in the y-axis. Now, whenever you have a problem with friction, the first thing you want to do is solve for the normal force. So in this case, the normal force is equal to mg, which is equal to 20 times 9.81, or it's equal to 196.2 newtons. We also know that the frictional force is equal to the coefficient of friction times the normal force. So that's equal to 0.5 times 196.2. So our force of friction is 98.1 newtons. Now the other thing you can do when you're looking for acceleration is take the two equations you found for the x and y axis, and you can add them and then get rid of t, so you can solve for a. So the two equations we have now are t minus f equals m1 times a, and m2g minus t equals m2a. So if we add those, we get t minus f plus m2g, that's a 2, minus t is equal to m1a plus m2a. These cancel out. Minus f plus m2g is equal to m1a plus m2a. And we now have these values. So this is a minus 98.1 plus 30 times 9.81 is equal to 20a plus 30a, or 196.2 is equal to 50a, or your acceleration is equal to 3.9 meters per second. Now we also want to know what the tension is in the string, and you can use either one of these two equations. So if we use the first one, T minus F is equal to M1 times A, tension is equal to F plus M1A, or tension is equal to 98.1 plus 20 times A, which we just found above. Or if you solve for that, the tension in the string is 176.1 newtons. And that's our answer for this problem. Let's do another problem. A man is standing in an elevator that, starting from rest, moves 2 meters upward in 1 second. He is holding a 3-kilogram package by a string. What is the tension in the string during the elevator's movement? So you can see the diagram here. We have an elevator, a man holding a package by a string, and the elevator moves 2 meters in 1 second. So let's do the free body diagram on the package. So we know its weight, which is mg, is pulling down, and the tension is pulling up, and the tension is what we're looking for. So if we add those forces, we get T minus mg gives us the movement of the package, or T is equal to mg plus ma, which in this case is equal to 3 times 9.81 plus 3 times a, or T is equal to 29.4 plus 3a. Well, now we need to find a, and we're given information in order to do so, and that is that the elevator moved 2 meters in 1 second. So using one of the kinematic equations, we find that movement y is equal to v0t plus 1/2 at squared. Well, in this case, v0 is 0 because the elevator started at rest. T is equal to 1 second, and y, the distance it moved, is 2 meters. So if we plug these numbers into our equation, we'll get our answer for A. So that's 0, and A becomes 2y over t squared, which is 2 times 2 over 1 squared, or our acceleration is equal to 4 meters per second squared. So plugging that in to that equation, we get T is equal to 29.4 plus 3 times A, which is 4, or T is equal to 41.4 newtons. That's the tension on the string in the elevator. Here's another problem. Two masses hang vertically, one under the other, connected by a string. The top mass has another string connected to it, pulling it upwards with an acceleration of 3 meters per second squared. The top mass is 20 kilograms and the bottom mass is 10 kilograms. What is the tension in the two strings? So we're looking for T1 and T2. So you can see the diagram here. Let's do a free body diagram for each of the masses. So for mass 1, we have the tension pulling up, and pulling down, we actually have the weight of both masses, mass 1, g, plus mass 2 times g. And for mass 2, we have T2, and in this case, the only mass pulling down, the only weight pulling down is its own, m2 times g. So we know that the whole system is accelerating upward with an acceleration of 3 meters per second squared. So let's apply the second of Newton's laws to the entire system. So F1 is going to equal the total mass times acceleration, which in this case is mass 1 plus mass 2 times acceleration, which is equal to 20 plus 10 times 3, which is equal to 90 newtons. So 90 newtons is the force pulling the whole mass up. Now we can concentrate on the masses independently and add up the forces. So for mass 1, the force on it is equal to the tension pulling it up minus the weight of the two masses pulling it down. And if we solve for T1, we get T1 is equal to force 1 plus mass 1 times G plus mass 2 times G. And we know these amounts. Force 1 is 90 newtons plus 20 times 9.81 plus 10 times 9.81. And if you work that out, you get tension in the first string is equal to 384.3 newtons. And now let's go back to mass 2. The force on mass 2 is equal to the mass times the acceleration of that system, which is equal to 10 times 3, which is equal to 30 newtons. That is equal to T2 minus M2G. So if we solve for T2, that's equal to force 2 plus M2G, which is, we just got force 2 up there, which is 30 newtons, plus 10 times 9.81, which is equal to 30 plus 98.1, or T2 is equal to 128.1 newtons. So now we know the tension in both strings for this system. Let's look at our next problem. A car travels around a banked curve at a radius r and at a velocity v. What is the banking angle theta? Well, you can see in the diagram the car on a bank, and let's draw the free body diagrams for the car. And again, this is the y and x axes. So in the y axis we have Fn cosine theta going up and mg going down, and in the x-axis we have Fn sine theta going outward and F mass times acceleration, centripetal acceleration, going to the right. So if we write these out, Fn cosine theta minus mg equals to 0 because the car isn't going up and down, and Fn sine theta minus ma equals to 0 because the car isn't moving along the radius. So Fn cosine theta is equal to mg, and Fn sine theta is equal to m, and acceleration is v squared over r. So if we then, and again we're looking for the angle theta, so if we then put one equation above the other, we put Fn sine theta over Fn cosine theta is equal to mv squared over r over mg. The fn's cancel out, the m's cancel out, and this becomes tan theta is equal to v squared over rg, or our angle is equal to the arctan of v squared over rg. That's the angle we need for the car to be able to go around the track. In our next problem, a 50-kilogram person is at an amusement park and goes on a ride called the rotor. The rotor has a radius of 10 meters. In the rotor, you put your back against a cylindrical wall that spins. The floor moves downward and you stay pinned against the wall, not slipping down. If the coefficient of friction between the person and the wall is 0.25, what is the minimum acceleration needed in order to not slide down the wall? And what is the minimum speed needed in order not to slide down the wall? So let's do a free body diagram of the person. Here's the person, and you have his weight pulling down. And what's keeping him from sliding down the wall is the upward force of friction. So we have the force of friction pulling up. And in the centripetal direction, you actually have the centripetal force, which in this case is equal to the normal force. So if we write down these equations, centripetal force is equal to mass times acceleration, which is also equal to the normal force. So that's equal to mass times v squared over r. So that's the centripetal motion. The force in the up and down direction, we can write those forces as the force of friction minus the weight is equal to 0, or the force of friction is equal to mass times g. And we know those numbers, so that's 50 times 9.81, or the force of friction is 491 newtons. So we also know that the force of friction is equal to the coefficient of friction times the normal force, which is equal to the coefficient of friction times mass times acceleration centripetal. And if we then solve for these, we get acceleration is equal to friction over coefficient of friction times mass. And we know those numbers. So that's equal to 491 from here. Coefficient of friction is given as 0.25, and the mass again is 50 kilograms, so that's equal to 39.3 meters per second squared. So this is the minimum acceleration needed to keep from sliding down the wall. Now we also want to know what the minimum speed is. Well, we know centripetal acceleration is v squared over r. If we solve for v squared, that's equal to acceleration times r, or v is equal to the square root of centripetal acceleration times r, which in this case is equal to the square root of 39.3 times 10. And if you do that calculation, you get v equals 19.8 meters per second, which is the minimum speed needed to keep from sliding down the wall. Let's do our last problem. A small rock is attached to a cord of length r and is being whirled in a vertical circle. What and where in its motion does the maximum and minimum tension in the cord occur? What is the minimum speed of the rock needed to keep the cord from going slack? So you can see this diagram, and it shows the rock going around in a vertical circle of radius r, and you can see the weight of the rock points downward. In this problem, we're not going to use an x and y axis. We're going to use a tangential axis, which is the force and acceleration moving with the velocity in a tangent to the circle, and the normal axis, which is the force and acceleration moving perpendicular to the movement of the rock. So let's look at our forces. So the force in the tangential axis is equal to mg sine theta. That's this force going this way. And the acceleration into tangential axis is equal to tangential force over mass, which in this case is mg sine theta over mass, or simply g sine theta. And in the normal direction, the normal force is equal to the tension, which goes that way, minus mg cosine theta. And again, the acceleration in the normal direction is equal to force over mass, which then would be t minus mg cosine theta over mass. Now acceleration happens to be equal to v squared over r. So this becomes equal to t minus mg cosine theta over mass. And if we then, or t is equal to m v squared over r plus g cosine theta. Now to find the minimum and maximum tension to keep the rock spinning, at the lowest point of the rock, which is on the bottom, we have theta is equal to 0, sine theta is equal to 0, cosine theta is equal to 1. So if we put that into these equations up here, we get at the lowest point where theta equals 0, we get the tangential force is 0, the tangential acceleration is 0, and we get t is equal to m v squared over r plus g. And that's the maximum amount of the tension we can get in the circle. So this is the point of maximum T at 0 degrees. Now, if we do the opposite, and if we look at when theta is equal to 180 degrees, we get the tangential force is equal to 0, the acceleration is equal to 0, but in this case, t is equal to m times v squared over r minus g, because sine still equals 0 here, but cosine is equal to -1 at 180 degrees. So this would be the lowest tension on the string at 180 degrees. For the next part, we want to know what the minimum speed is to keep the rope from going slack. So what we really mean is we want to know when the tension is greater or equal to 0. So if we set tension equal to 0, we know that's equal to mv squared over r minus g at the minimum point. Then we get mv squared over r is equal to g, m times g. V squared is equal to rg, or v is equal to the square root of rg. That's the minimum velocity we need to keep the cord from going slack.